Okay, it's a great pleasure to have Vincent Bouchard here with us, who did his undergrad at UDM. He did his PhD under Philip Candalis at Oxford. He's well known, of course, for his work on Calorie-Yau manifolds. And Vincent is a professor at University of Alberta, and I myself was overlapped at Alberta a little bit, and he's well known for his lectures, first year calculus lectures, which are on YouTube, which integrate mathematics and music. They're quite popular with the U Alberta first years, so you can check them out on YouTube. And I think Vincent characterizes himself as a, remember you gave a talk where you said you do physical mathematics. So hopefully he'll be talking about some of that today. So thank you for giving the talk today, and please go ahead.
Thank you very much for the invitation and the introduction. Yeah, if you watch the YouTube video, good luck. I'm an awful singer, so so good luck. But yeah, let's talk. So what I'm getting to, yeah, physical mathematics. It's a very good starting point. In fact, I'll mention that and the beginning of this talk. But title of this talk, as you can read, is Transalgebraic Spectral Curve. By the way, I'll use the word transalgebraic a number of times today just because I find this word so cool. But I'll try to define what it means at some point. Yeah, transalgebraic spectral curve, quantum curves, and Atlantes Hurwitz numbers. There's a lot of buzzwords in there: quantum, Atlantes, transalgebraic, spectral, and it should make all of you pretty excited. So that's good. So this is what we're going to talk about. But what I'll do is first just provide a motivation. So the talk is about physical mathematics, as I said. So the idea of physical mathematics in my mind is to use physics to do mathematics. So we want to be inspired by physics, use concept or dualities or things like that in physics to do pure mathematics. The goal is really to study mathematical concepts and mathematical structures, but using ideas from physics. And this is exactly what this project that I'll talk about, which is, by the way, joint work with Reinier, who's a postdoc at the U of A, is present right now, and Quinten, finishing master's student at the U of A, who's a very strong master's student, by the way. If you are interested in a PhD student, I think he was applying just right now to McGill, if I remember well. But in the case, I don't think he's here right now. But yeah, so this is joint work with them. Should be published soon, not published yet, but should be very soon. So the starting point is going to be some motivation, as I said. So I'm just going to motivate this from physics. Now I'll be very, very rough here. I don't want to explain any details of this. This is just to give you a motivation for the main topic of this talk, which I call the topological recursion, quantum curve, correspondence. So the starting point is, or at least the motivation for the subject is in physics, more precisely in what's called matrix models. So most of you are probably familiar, at least to a certain extent, with what matrix models are. So you can think of it in a number of ways: random matrix theory in mathematics, or matrix models in physics, or quantum field theory in zero dimension, if you want. It's basically just integral over spaces of matrices, mostly Hermitian matrices, which is what we'll be mostly focusing on. By the way, I did not mention at the beginning, but as always, if you have questions, please interrupt, because we're not in person, so I can't see you. So just interrupt me. Or I also have the chat box open, so you can use the chat. I will see it if you feel that you don't want to interrupt, but feel free to stop me anytime.
Okay, I will stop you. Is transalgebraic the same thing as transcendental?
Well, it will be basically a function. Transalgebraic function, in my definition, will be just a function with exponential singularities, so essential singularities. So yeah, it's related. It's just, I mean, it's defined in some papers of some mathematician, and he calls these things transalgebraic, and I thought it was a fun word. So we borrowed it, but you'll see, I'll explain this in a few slides. It's something you know very well. It's nothing fancy. Okay, so if we start with matrix models, in the context of matrix model, there's kind of two types of observables that you can construct. Natural observables you can construct. One of them is what's called the correlation functions of your matrix models. And these are basically just expectation values of traces of matrices. As I said, I'm not defining any of that here on purpose, because this is not the goal of this talk. I just want to give the motivation for the goal of the talk. So So these are objects which are basically obtained by integrating over space of matrices, these kind of things, traces of matrices. So these are generating functions for all possible products of traces of matrices. And in matrix models, we want to build observables or gauge invariants. So we basically want to build them out of traces and determinant. So this is one example of a whole set of observables, correlation functions. And it is well known that they basically are determined completely recursively. And this was known for a long time. You can formulate that in terms of word identities for your matrix model or loop equations, all kinds of different ways of saying the same thing. Or you can write down a full solution very explicitly, which is basically what has become known as the topological recursion, which was formulated by Chekhov-Eynard-Orantin here, but as we'll see, it applies much more broadly than just for matrix models. But the origin is here in calculating these correlation functions. On the other hand, there's another type of observables you can construct. Again, you want things that are gauge invariants, so determinant is another possibility. And you could construct these kind of observable here, expectation value of determinant. So x and x1, xn here are just variables here that index generating functions that are used to generate, to write down a generating function. And these observables, this observable here, which I'm going to call psi. So these ones here I should call wn. So this one I'm going to call psi is just expectation value of determinant. And it's also known to satisfy a whole bunch of things in the context of matrix model, things like determinantal formula, which will give rise to what I will call the quantum curve. So the idea here is that there's a relation between these two. This is something that is, again, well known in the context of matrix model. And the relation is actually quite simple. It follows from one of the most famous relation between determinant and trace, which is that determinant is equal to exponential of trace of log. So you see, if you kind of integrate this very, very roughly speaking, if you integrate these things, you basically end up with some things that involve traces of log. So if you take an exponential of a sum of integrals here, you basically can rewrite it in terms of determinant, which is basically your psi here. So all this to say that using this and a lot of manipulations and so on, you can write psi in terms of correlation functions. Again, this is something that is known in the context of matrix model. And because psi satisfies a whole bunch of things, in particular what I will explain or define as a quantum curve, and Wn satisfies a recursive structure, which will become this topological recursion, this relation here, determinant equal exponential of trace of log, gives rise to a relation between topological recursion and quantum curve, which is what I will call the topological recursion quantum curve correspondence. Okay, so this is the motivation for the title. Oh, actually, it's not in the title anymore. I used to have, last time I gave a similar talk, I had TRQC correspondence in the title. So this was to motivate the title. Now I'm not motivating the title, but I'm motivating the topic of the seminar, which is this correspondence. And the origin is coming from matrix models. But the whole point here is to not stay within matrix models, because that would be fairly boring, or at least, I mean, it would be interesting, but it's already well known in this context. So this is the idea of physical mathematics. Now you take the inspiration, use physics as a source of ideas, in this case, matrix models. In matrix models, you see from fairly simple considerations that you have a relation between a recursive structure, which will become known as topological recursion, and another structure that we'll call the quantum curve. And that's fairly straightforward to at least argue that this should exist in the context of matrix model. And now we want to argue that the same correspondence should exist in a much, much larger setting in pure mathematics. So that's the idea of the talk and the idea of the topological recursion quantum curve correspondence. Okay, so the starting point is to abstract these two things away from matrix models. And this was already done. In particular, the topological recursion side. This is something that by now is well known. This was done in 2007. Originally, the first paper was 2007, but it's based on previous papers with Chekhov as well, which is not why it's often called CEO, topological recursion. So Eynard-Orantin, basically what they realize is that this recursive structure that in the context of matrix models calculates the correlation functions, it can be completely abstracted away from matrix models. It's a purely kind of mathematical structure or recursive structures. And then you could say, well, you can apply it much more generally to spectral curves. And you can ask whether that is calculating something interesting if there is no matrix model behind. So this is what they did in 2007. They formulated the kind of general framework of topological recursion. And basically, well, they showed that in some cases it was calculating interesting thing and asked whether this was more general. And for some reason, I mean, this paper is amazing when you think about it, because there was such a, I don't know how to say it, but it was very deep to think that actually that structure might apply in such a large number of different contexts, which is exactly what happens. Now we know that the topological recursion is kind of a, I wouldn't say universal structure, but it's something that appears in many, many different contexts. And by now we have a better understanding of why, but at the time it was quite mysterious. So it was a fantastic paper. But what has become known since then, so this was 2007, so there's been a lot of work on this since then. So it's become known that these Wn that I had before, even if there's no matrix models or anything behind, they are often interesting, and they generate all kinds of enumerative invariants. So they could generate, for example, Hurwitz numbers, Gromov-Witten invariants of some target spaces, not invariants in some other context, intersection numbers, as I've said it, on moduli space of curves, R-spin moduli space of curves, all kinds of different things. All these different enumerative geometric problems can be kind of recast in the same recursive framework, which is quite remarkable. So that's the topological recursion side. And now if we can also abstract away from matrix model the relation between topological recursion and quantum curves, so in other words, the relation between correlation functions and the expectation value of the determinant in a matrix model, that might lead also to some very interesting properties for these invariants, because one side has a nice enumerative interpretation. So the other side would give some sort of a structure to this interpretation, which will be closely related to integrability statements in enumerative geometry. So that's the goal of the project, or of the correspondence. Okay, so hopefully I've motivated in at least some sort of way that makes it interesting. And now let me tell you what I'll do. So what I'll now do is explain these things in some detail. So I'll try in this talk to be very kind of non-technical. I like to do this in general, although often I think I am non-technical and I end up being technical. So please stop me if I am too technical. But I think it's I'll try to emphasize the conceptual aspects more than the computational aspects. So hopefully I won't put too many formula, the complicated formula, because it's easy, especially with topological recursion, to write down very complicated looking formula that mean nothing to anyone except the experts. So I'll first define what topological recursion is, very broadly speaking, and then I'll explain what this correspondence should be. So I'll define what quantum curve stands for. And then I'll talk about the work that we're doing with Reinier and Quinten, which is about generalizing this to what I call transalgebraic spectral curves. So basically, these are the spectral curves that give rise to the Hurwitz numbers in enumerative geometry, and R-spin Hurwitz numbers, and all these kinds of Hurwitz numbers. And so that will be the last two topics of this talk. Okay, so let's get started with explaining the topological recursion. So the starting point of topological recursion is a geometric object, which we call a spectral curve. Now, there are many ways of defining a spectral curve, and the way I'll define it is perhaps the most common one in the context of topological recursion, but there's many other ways of thinking about it. So for me, an algebraic spectral curve, so I'll add algebraic here, we'll see why in a second. So an algebraic spectral curve is basically four things: Cx, W01, W02, such that C is a compact Riemann surface, so a sphere, torus, whatever. X is a meromorphic function on the whole compact Riemann surface C. W01 is meromorphic one form, and W02 is a symmetric bilinear differential. So here I should specify more things on this, but it's not going to play any role in the talk today, so I'll avoid being too technical. Those who know about topological recursion know that this should be the Bergman kernel, blah, blah, blah. Okay, so the key point are the first three objects for us here. And now I'm assuming that X is meromorphic on a compact Riemann surface. So you can think of it as, instead of thinking of it as a function, you can think of it as a finite degree branch covering, right? So that's always possible. Because it's meromorphic on the compact Riemann surface. So you can think of it in this way. And then the main feature of this branch covering that will play a special role in topological recursion is the ramification points of the branch covering. So if you take any point on your compact Riemann surface, well, you can always write down a local normal form for your map. This is just very basic geometry. So you can write your map as being sending a local coordinate around the point to some power of it for some integer m. And then if m is more than 1, then this is called the ramification point. That's the standard definition. That just means that you have, if you think of the different sheets of the mapping here, so at the point P, there's at least 2 sheets. Well, there's exactly m sheets that meet at this point. So these points will play a very, very special role in the formalism of topological recursion. So I'll call R the set of ramification points of the branch covering C, which is defined as part of the data of a spectral curve. Okay, so this will be important. So that's why I spent a few minutes defining this. Now, there's a few things here that I should say about algebraic spectral curve, which makes them nice. First is that if your C is compact and W01 is meromorphic 1 form, you can always write it in this way because X is also a meromorphic function. So this is a meromorphic 1 form. So you can always write it as y dx, where y is another meromorphic function on your compact Riemann surface. Okay, so instead of defining the data of a spectral curve as being Cx and W01, I could have said Cx and y. So 2 meromorphic functions in C that would be completely equivalent. And also because these are meromorphic on a compact Riemann surface, we know that they satisfy an equation and that this equation is algebraic. So in other words, this is a polynomial equation here. So this is why these are algebraic spectral curve. Okay, so the typical example that you can keep in mind is just the very simple branch covering. If you take X to be just the R fully ramified branch covering at 0 and infinity. So Z here, this is meant to be a branch covering on the whole Riemann sphere. I'm just writing it in one coordinate in one patch, but that's, you can extend it to infinity. And then you take Y equals to Z. Then these satisfy, of course, a polynomial equation, which would be just y to the r minus x equals to 0. And that's called the Airy curve, the R Airy curve. And the topological recursion we're going to formulate turns out to generate R-spin intersection numbers. If you apply it to that spectral curve, it constructs generating functions for intersection numbers in the moduli space of curve with R-spin structures. The famous problem studied by Quinten and then Kontsevich and Zwankin and friends. Okay, so that's the starting data of topological recursion. Now, what is, so any question on this so far? That's should be fairly basic for those of you who know about topological recursion and understandable for everyone else, hopefully. Okay, so topological recursion now is a kind of a magic beast or some big machinery that does something for you. So what it does is the following. So you start with a spectral curve, which is just what I introduced. So that's your starting data. Out of this, so topological recursion here is basically a big formula. In this formulation, it would be just a big formula that constructs some object that I will call WGN. So let me introduce some notation. So Z here is meant to be a local coordinate or some coordinate on the compact Riemann surface. So remember, a spectral curve here is 4 things. And in particular, there's a compact Riemann surface C here. So everything here that I'm constructing WGNs will be forms, differential forms living on a compact Riemann surface. In fact, there are symmetric differential forms living in this case on n+1 copy of the compact Riemann surface C. So here there's Z0 and Z vector stands for Z1 to Zn. But the key point here is that we're going to construct these objects by taking a sum over all the ramification points of the branch covering C, and then we do some contour integrals around these ramification points, so in other words, we pick residues at these ramification points, here there's some sort of recursion kernel, which I will not define because if you know about it, you already know it. If you don't know, you're not interested. And then there's an object here, which is a complicated combinatorial object. But the key point is that it's defined entirely in terms of WGN or WG prime N prime with 2G prime minus 2N prime plus 1 less than 2G minus 2 plus N. So that's a fully recursive structure. So here I should say as well, G is greater or equal to 0 and N is greater or equal to 0 in this notation here. So this is a fully recursive structure in the sense that if you know all the WGNs for a certain 2G minus 2N plus 1, sorry, 2G minus N plus 1, there's no 2 here. What am I doing? That should be the minus the early characteristic. So once you know all of them for a certain 2G minus N plus 1, you can use that to construct the next one. So you can build all this sequence recursively, and all you need is the initial conditions of the recursion, and these are given by W01 and W02, which is part of the data of your spectral curve. So in other words, just to summarize here, so you start with a spectral curve, and then you construct a sequence of object, which I call WGN or WGN plus 1. So if you write it like this, then G would be greater or equal to 0, N would be greater or equal to 1. And these are now symmetric differentials on N copies of the Riemann surface C. So that's topological recursion. Now, of course, the key of topological recursion, all the interesting stuff is in the particular definition here, but I'll avoid writing it down just because it's complicated and it would take me a while. But there's the key feature as well is that it involves residues or contour integrals around the ramification points. Okay, and the other thing that I want to say is that these here are basically the objects that encode the interesting enumerative invariants. So what happens is that if you choose interesting spectral curves, then the WGNs are symmetric differentials, but you can expand them as Taylor series around some points, say the ramification points or potentially infinity or whatever, and then the coefficients will give rise to interesting enumerative invariants. In fact, usually there's two types of expansion. If you expand at the ramification points of your branch covering C, then you can show that the coefficients can always be written in terms of integral over the moduli space of curves. While if you expand at a different point, potentially infinity, then you might be able to rewrite them as things like Hurwitz numbers or Gromov invariants. And because these are the same WGNs, in fact, this gives you a relation between these two types of invariants, which, for example, in the context of Hurwitz numbers would be the LSV formula, for Gromov invariants would be localization formula, and so on. So you get all kinds of nice results directly just from the construction of these WGNs from topological recursion.
Could I just interrupt 1 second?
Absolutely.
So I know you're going to generalize this, but so far, is C always compact?
Is C always compact? Yes. For
is
this
it
point
always
of view,
a branch cover of the Riemann sphere?
X, no, it doesn't have to, well, X is always a branch covering of the Riemann sphere. Yeah, but C doesn't have to be a Riemann sphere. Could be a...
No, I know. So, but you're going to generalize this, but the usual setup is that, right? That C is compact and it's branched over the Riemann sphere. Well,
so it depends. I mean, for example, for Hurwitz numbers, the spectral curve is not algebraic in that sense because X would have exponentials, so it wouldn't be meromorphic on the Riemann sphere. So you could either define this as saying C doesn't have to be compact, which is the way that usually people do it, but I want to keep C compact, so I'll allow X to be non-algebraic or transalgebraic.
But will you, throughout your talk, always have a branched cover of the Riemann sphere?
It will always be a branch covering of the Riemann sphere, yeah.
Okay.
Topological recursion is always defined for branch covering the Riemann sphere. As far as I know, I don't know how to define it if the base is not the Riemann sphere. Okay, so now this is the topological recursion side. Now I want to talk about the other side, the quantum curve side. So remember, this is now, we're trying to abstract away from matrix model the relation between determinant and log. Determinant is equal to O trace, determinant is equal to exponential of trace of log. which was giving a relation between an object I call psi and the object I call Wn in matrix model. So Wn now are replaced by these WGNs constructed by topological recursion. Now I want to construct an object which replaces the expectation value of determinant, which was the psi here, which I will call the wave function. So the idea is the following. So you start with a spectral curve.
Okay, I can't resist. I have to ask also.
Yes.
So psi, of course, for someone who likes tau functions as I do, psi is the Baker function. But is it always a Baker function? And is there always a tau function?
Yeah, so basically, is there always a tau function for arbitrary spectral curves? So I don't think this is known, is it? I don't know. I mean, you're absolutely right. Psi will be the Baker-Akizar function of the corresponding tau function if there's one. Whether there is always a tau function, I don't know. I mean, in the case, the example I had before, the R-spin Hurwitz number case, then yes, then it would be an RKDV.
Well, I know that Bertrand would immediately say yes. However, what he means by tau function is much more general than what we mean by tau function. So
Right.
That's why I always ask that question.
Yeah, and yeah, I don't know how to answer it more than what Bertrand would say. So. Okay, so here is going to be maybe the only complicated formula I'm going to write, but it's not complicated. So I just want to write now how you can construct this psi, because it's important for the correspondence, out of the WGN. So the idea, again, this will look like a complicated formula coming out of nowhere, but if you look back at the matrix model motivation, that's exactly what you're going to get. So from your spectral curve, you construct these WGNs, and then the idea is you want to construct a big object psi, which will be a sum over all WGN, but more precisely, you just introduced a parameter h bar here, some n bar factorial, and then you integrate. Remember here, to get the log, we had to integrate a WN in matrix models, so we're doing something similar here. We integrate here the WGNs, and there's like a small modification here for g equals to 0 and n equals to 2. We need to remove the pole, otherwise this would not be well defined. So I should write this down, but that's not very important for us. Okay, you get something like this here, which, so that's a 2, sorry. That basically constructs, if you're given a sequence of WGN, you can construct this object psi uniquely in this way. It's not quite unique. There's a choice here of base point for your integration. And in fact, it does play an important role in the correspondence, but I won't not have time to talk about this. This in principle should be a pole of X or something like that. It's more general choices that are allowed, and this can be generalized as well. But the idea is that this object here will be, will kind of replaces the expectation value of the determinant in the context of matrix model, and it will play the role of a wave function. It will be the solution of a quantum curve equation, which is what I'll write in the next slide. I should mention as well, this formula here is only expected to hold when C is a genus 0 Riemann surface. When it's higher genus, you need to modify this, add some non-perturbative corrections, but that is not something I will talk about today. Okay, and then the quantum curve conjecture is the following. Is the statement, it's a conjecture in general, it's a statement that there exists a quantization of P. So remember, P is the polynomial equation of the spectral curve. So now you quantize it. Quantizing means that you turn it into an operator by replacing X by X hat, which is just multiplication by X, but Y by Y hat, which is H bar ddx. So the commutation relation here of these two is H bar. And then the statement is that there should exist a quantization that kills the wave function I just constructed. Now, I should be a little more precise here. I mean, what do we mean by a quantization? So what we mean is something like this. So if I write it like this, and then there's also possible powers H bar. So what I'm saying here is that the leading term should be just the original spectral curve equation with normal ordering. So all the H, the dx on the right of the X. And then you can have H bar corrections. So you can have things like this for some polynomial equation here. Now there's some constraint here. The degree here has to be less than the degree here, something like that. Otherwise, the conjecture would be pretty much empty. But roughly speaking, that's what it is. I mean, what happens in general is that you start with your polynomial equation, and then you quantize it, which means you turn the x and y as operators. But of course, there's no unique way of doing that because there's the different choices of ordering when you make things non-commuting. So if you choose different orderings, it'll give you h-bar correction. So that's why there's this here. But there should exist such a quantization that kills the wave function. That is the topological recursion quantum curve correspondence. And that's what is true in matrix models. And then we want to see what it has true in general, what it holds in the very general context of topological recursion. Okay, so what is known about this? This has been studied for many years, so there's quite a few things that are known. So the first many papers on this subject were basically proving this correspondence for all kinds of specific cases. Case by case. So it was always kind of a similar calculation, but in different contexts. You start with topological recursion somehow, or you start one way or the other. You basically do a lot of complicated calculation and show that you get the same thing. It was always compact Riemann surface of genus 0. So here's a few papers: Gukov, Sulkovsky, Mulaze, Shadrin, Spitz, Mulaze, Norbury. A lot of people worked on that. For high genus spectral curve, then, as I said before, the conjecture needs to be modified. This is known not to be true for high genus spectral curve, but you can make it true, at least conjecturally, using a non-perturbative formulation of this wave function psi. And this has been studied by a bunch of people here. In a paper of Bertrand and myself a few years ago now, 2016 maybe, I don't know. We proved that the conjecture is true for a large class of genus 0 algebraic spectral curves, so a very large class of spectral curve, but are still always genus 0 and algebraic. And this was generalized, in fact, a few months ago, I think, by these people: Elba Garcier, Marshall, Orantin, and it should be Eynard, no?
Yes, it is.
Yeah, so no, Garcia Falde and Eynard, sorry, but Garcia, whatever I talking about. So anyway, these four people proved it recently for all genus, so any genus, but still algebraic spectral curve, with the condition that simple ramification. So basically, there's more and more results here that show that it seems like this is true. This conjecture is true, at least to some generality, but it's always focusing on algebraic spectral curve.
So when you say algebraic curve, do you mean P is a polynomial?
Yeah, so two ways of thinking about it. One is that P is a polynomial, which is completely equivalent to saying, and that comes back to your previous question, that C is compact Riemann surface and X is X and Y, or X and W01 are meromorphic on the whole compact Riemann surface. So that's equivalent to saying this satisfies a polynomial equation. So Hurwitz case, for example, is not part of this, or Gromolden case.
Well, some of Hurwitzes are certainly polynomial Hurwitzes, polynomially weighted Hurwitzes.
Oh yeah, no, sorry, yeah. I mean, for example, the simple Hurwitz numbers or completed cycle or these ones. No, you can have some types of Hurwitz numbers are polynomial. Yes. Okay, so now what about transalgebraic spectral curves? So what are transalgebraic spectral curves? I mean, they're sexy, but aside from that, what are they? So here's a definition. It's just a beautiful word to mean something very simple. So yeah, it's the same thing. You start again, I want to keep C a compact Riemann surface, but now I don't want X to be meromorphic on C. So what I want it to be is what I call a transalgebraic function, which again is from some obscure paper that this is called transalgebraic function. But it's just a function here which may have isolated exponential singularities. So that's the definition here. So the example that I will keep in mind for the rest of this talk is the following. If I take X, that's not an X, that is an X, as being Z e to the minus Z to the R for some integer R. So as those of you who know about topological recursion know, this is the spectral curve here that I will construct gives rise to Hurwitz numbers with completed cycles, so R-spin Hurwitz numbers. Okay, so that's this transalgebraic thing, but I still require that W01 is meromorphic on the compact Riemann surface, and W02 is the same. But now there's, of course, some key differences with the algebraic case, because X now is not a finite degree branch covering anymore. If you think of it from the compact Riemann surface to the Riemann sphere, then it's not finite degree anymore. So it has, if you want, infinite degree, right? Because there's an exponential here. So that changes the behavior quite a bit. And if you think of the ramification points, then it will have some finite ramification points as always. So there's some points here where you can write a local normal form as always, but it also has exponential singularities. In this case, it's only one at infinity, but you could potentially have more than one. Okay, so that's the general behavior of these curves. And you can think of exponential singularities as somehow infinite ramification points, right? All the infinite number of sheets meet at the exponential singularity. Good, so this is not new. This has been studied for, I mean, not just in mathematics, but in the context of topological recursion, this has been studied for years. So you can, oh, before I do that, I should mention something. So as part of the differences here, there's also the fact that W01, you can also redefine a y, but you have to be a little careful here. So x is a transalgebraic function, so it has exponential singularity. That means that dx is not meromorphic on C, but d log of x is meromorphic on the Riemann surface. So if you're given a meromorphic one form on C, you can always write it as y d log of x, where y is also a meromorphic function on C. So the only difference here with before is that it's d log of x instead of dx. But another difference is that it doesn't satisfy a polynomial equation anymore. So because y is meromorphic, but x is not, so they do satisfy an equation, but it will involve exponentials. So again, if you take the example that I had before with your x here, but suppose I take y to be just z, which is again the case that will give rise to R spin Hurwitz numbers, then the equation to satisfy would be x. Let me write it like this: e to the y minus y equals to 0. So that's the general behavior. Here you don't get a polynomial equation, so that's why we don't call them algebraic, but transalgebraic. Okay, so what I was saying is that these have been studied for a while in the context of topological recursion, and you can certainly apply topological recursion to these curves. There's no problem. What usually people do is that they only consider the finite ramification points, and they use the exact same formula. And you construct with the same formula, with the same residue at the finite ramification points. You construct a sequence of WGN. So it gives rise to some WGNs in the same way as before. These WGNs are still symmetric differentials, meromorphic on the compact Riemann surface. And in particular, if you take this example, then it was shown and proved by people here. So this is Tunin, Balkovsky, I think Reinier, right? You're on there?
There.
Shadrin and Husby?
Popolitov.
Popolitov, yeah, exactly. So you guys proved that the WGNs here are indeed generating functions for R spin Hurwitz numbers or Hurwitz numbers with completed cycles, which were studied by Okunkov-Pandaripande many years ago in the context of relative Grommelton theory of P1. So that's a particular type of Hurwitz numbers where instead of having, you have a complicated ramification at infinity, arbitrary ramification at infinity, and instead of having other points which are simply ramified, then you look at points that are ramified with what's called completed cycles, ramification profiles. Anyway, you can define that combinatorially. The definition is not important for now, but they are interesting, and they are calculated by the spectral curve. If you apply topological recursion only to the finite ramification points. Okay, cool. But is that the end of the story? So what we claim is that this is not the end of the story. This is not actually, you can do better than this. What do I mean by that? Is that the definition of topological recursion of these curves is actually problematic in some way. I mean, it works, there's no issue, it's consistent, but it's not nice. It's something that is not good with the definition. So let me try to explain what happens. So if you take this example, we'll just do it for this example, but you can do it for any transalgebraic spectral curve. So if I call this my spectral curve S, what you can do is you can consider a sequence of algebraic spectral curve that converge to this one, right? That's a very natural thing. If you have an exponential, you can realize it as a limit. So I could construct a sequence of spectral curve here that would be something like this. and then I have the same y. So let me call them S n, capital N. So sorry, that should be a capital N here, right? So these are just algebraic, right? You could write down a polynomial equation for all n here that these satisfy, so it's completely algebraic. And clearly, you know that in the limit, this spectral curve here will converge to the one above, right? That's just standard definition of the limit of the exponential function. So this will converge to S.
Yeah, just a quick comment. Even r equals 1, which is what the first thing that Okounkov and Panderpanda study, that's already transalgebraic, right?
Exactly. This would give rise to simple Hurwitz numbers, so no R spin, and that's already transalgebraic. Yeah.
Right, but there also you can have a sequence which gives the exponential, and it actually is just the what is it? The I guess the weakly monotonic.
So in this case, so I mean, it's just a particular case here where you set R equals to 1. So in this case, our construction will give the same thing. In that particular case, the same thing as the original topological recursion. So there's no, it's kind of a special case. It just happens that for R equals 1, there's no difference between what I explained in the next few slides and what was done already before. But that's only for R equals 1. It's kind of a, yeah, it's just a coincidence, really. But I mean, it'll become clear. I'll mention that soon. Okay, so the key point here is that, well, I'm constructing a sequence of algebraic curve that converge to the transalgebraic one. You can always do that for any transalgebraic curve because you only have exponential singularities. You can always do that. And then there's an actual question, right? If you construct the WGNs from just the standard topological recursion associated to the sequence of spectral curves. So for every n, I construct the WGN. I can also construct the WGNs associated to the limit curve, the transalgebraic one, using the standard definition of topological recursion that only keeps track of the ramification points. And then you can ask, well, I mean, does the limit commute with topological recursion? Is the WGNs of the limited curve the same as the limit of the WGNs you construct for the sequence? I mean, you would like this to be true. It's a nice property. So if you're constructing a framework in general, you want it to be as nice as possible. So you would want this to be true. But the answer is no. This is not true, except for R equals to 1. But that's just a miracle in that particular case. So in general, this is not true. So the limit doesn't commute. The WGN of the limiting curve, the exponential curve, basically those that generate Hurwitz numbers, are not equal to the limit of the WGNs of the sequence. So to me, what this shows is that there's an issue here with the definition. Probably, or put it differently, probably we could define topological recursion in a different way so that this is true. And that's exactly what we do. That's what I would call the transalgebraic topological recursion. So what is it? So I'm not going to define it because it's again fairly technical, but the idea is exactly what I just said. So we propose a new topological recursion, which is, let's call it TA here for transalgebraic. So it produces a sequence, and it's very similar. It's the same formula, but the main difference is that we also include exponential singularities. Instead of only taking residue at ramification points, we also have contributions from the exponential singularities. And if you define this, then it's defined in such a way that it commutes with the limit. And the key point here is that the way we actually define it is by proving that the limit here of the sequence converges. So this is a well-defined object, but what you see when you study this limit is that the limiting object here have poles at the exponential singularities. So that's why you need to change the definition of topological recursion when you work with transalgebraic spectral curve. You have to include contributions for the exponential singularities, otherwise there's no way that this equality would ever be true in general. And roughly speaking, what our definition looks like, so it's hard to write down because, again, there's issues with convergence and all kinds of things. Very roughly speaking, what happens is that it looks pretty much the same as the standard definition, but here in R, we include not only the finite ramification point, but also the exponential singularities. Now, that leads to some convergence issues, as I said, because if you know about topological recursion, you know that the integrand here is basically symmetrized over all sheets that meet at the ramification point. And if it's an exponential singularities, you have an infinite number of sheets. So these are infinite sums here. So you have to make sure everything converges and so on. But we can prove that the limit here is converges, and there's some nice, it has some nice properties, which basically amounts to saying that this is well-defined and produce some well-defined sequence of WGNs, which are exactly equal to the limit of the WGNs for the sequence of curves. Okay, so that's basically our new construction here, and it's tailor-made such that this equality is true, right? We want this equality to is true, so we construct a generalization of topological recursion that makes it true. Now, of course, if you're looking at an algebraic spectral curve, it's the same as before. So it's only different when you have a transalgebraic spectrum, when you have exponential singularities. And what you can show is that in the particular case of the R-spin example, the one I had before, you can show that, in fact, the contributions you get from exponential singularities are very special. So only the WG1s turn out to have poles at exponential singularities. They have a very nice form. You can write them very easily in terms of some basis of one forms at the exponential singularity. So they're very simple, but they are there. You cannot ignore them. So you can calculate them very explicitly. Okay, so what's the upshot of all of that? So one upshot is that we now have for free a proof of this topological recursion quantum curve correspondence for all these transalgebraic spectral curves using our transalgebraic topological recursion. So why? Well, just because it commutes with the limit. So what we do is just the following. So if you have, you can construct a wave function for any finite n. So this is an algebraic spectral curve. You construct the WGNs, construct the wave function, you take its limit. By construction, it's going to be the same as the wave function of the limiting spectral curve. And then for any finite n, we know that these satisfy the correspondence. So there exists a quantization that kills these psi's. So this was proved by myself and Bertrand for a large class of those, and also by Elba and Bertrand, Nicolas, and Olivier recently for pretty much all spectral curves with simple ramification here. So we basically have now, we know that the sequence satisfies the quantum curve. So to get the quantum curve for the limit, we just take the limit of the operators. So this is basically straightforward. We don't have to prove anything. It's given for us. So we have now a general proof for transalgebraic spectral curve. And if you take this favorite example, for example, so if you construct this sequence, so remember the sequence here was xn is equal to, so if I write it in terms of, I just write it in terms of parameterization before, but now if I write the actual algebraic curve satisfied for every finite n, you get something like that. And then this, for this class of curves, you can construct a quantization that kills psi. This is known. In fact, this falls into the class that I studied with Bertrand a few years ago. So you can construct this for finite n, and then you can take the limit as n goes to infinity. And you end up with the statement that this operator here, which is the most straightforward quantization of this curve, where you just replace y by y hat and x by x hat, where y hat is h bar. Here there's x ddx instead of ddx, because remember, we have to think of log x as being the right thing here. In any case, you construct this quantization here, and basically our theorem is that this kills the wave function. But this is the wave function constructed from our transalgebraic topological recursion, not the one constructed from the original one. There's difference because of the exponential singularities. Okay, so this is cool. This is a proof of topological recursion quantum curve correspondence in that setup. But topological recursion is interesting because it calculates nice enumerative invariants. So the natural question is, what is our generalization calculating? And in some way, that's even cooler. So here's what happens. So in our typical example, I've already mentioned a number of times that if you take that spectral curve and now you apply the standard topological recursion, you construct a sequence of WGNs, and these are generators generating functions for Hurwitz numbers with R-spin structure or completed cycle Hurwitz numbers. This is known. Now, our transalgebraic topological recursion calculates something different, right? So what is it calculating? So the first thing you should ask is how does that relate to this? So it turns out that for this case, the quantum curve was actually constructed as well. But it was not constructed from topological recursion. As I said, no one knew how to relate topological recursion to quantum curve when you have a spectral curve that has exponential singularities. But using other methods, basically combinatorial methods related to Hurwitz numbers, you can actually construct an operator that kills the wave function here, but it turns out to be this complicated mess, which was proved by Mulaze, Shadwin, and Spitz. And that kills the wave function associated to this curve, but with the usual topological recursion. Now, this is also a quantization of this curve, but it's a fairly complicated one. It's like a very weird choice of ordering. But if you replace y hat and x by commuting variables, you'll see that this reduces to that. So it's a quantization of this. It's just a very strange choice of ordering. While if you compare our choice, the one we get from Transalgebraic is the very straightforward quantization. So again, it shows that probably a definition we're working with is kind of more natural in some way. Yeah, but in the case, we have a psi here. Yes, there's a question.
If y is ddx, the r equals 1 case is just a finite difference operator. Can that be done for different for higher r's?
Can it be done?
Spectral curve, a finite difference equation.
Well, here it's also, I mean, it's, yeah, so how do you write that? If r is higher, then you have exponential of higher order derivatives. That's still a difference equation, right? I mean, it's not, this is not a difference equation, by the way, because there's also a y here. So it's a kind of a mix of a differential and a difference equation, even for y equals to 1.
Right.
But yeah, you can still write the action of the exponential as a difference operator, as a shift operator. Is just more complicated, I think, right? If r is greater than 1.
What's telling you what to represent as a difference operator and what to represent as a multiplication operator?
Yeah, so that's just a choice. I mean, which of the two we use as x and y? I mean,
yeah, because here the simplest choice would seem to be that y should be the multiplication operator, and then that's just a first order differential equation.
Yeah, so but in topological recursion, you see y, I mean, this is part of the conjecture, the topological recursion quantum curve correspondence. So, you know, x and y play a very different role in topological recursion. Mm-hmm. X is the branch covering, right? Its ramification points are essential. Everything is formulated in terms of that. Y is kind of a kind of auxiliary thing that just enters in the initial condition, the W01. Mm. So they play a very different role, and that's also shown here. So you know, in the statement of the correspondence, you want y to be the difference, the derivative operator, not x. Okay. Otherwise, it's not expected that you would get any of that. So I guess that comes from the structure of where topological recursion comes from in the matrix models in the original setup and so on. You could probably argue why this is the case, but yeah.
Maybe I could just make a very quick comment. There's another setting, of course, for quantum spectral curves, which is much older than topological recursion, and that's the functional beta ansatz. And there, it's clear because you have a classical curve, which is really just the characteristic polynomial of a lax matrix that depends on the parameter, and the guy that becomes a derivative is the eigenvalue, not the loop parameter, but the eigenvalue. So that's a different context. But I think it's essentially for the same reason that that's the one which is ddx.
Yeah, and I think in the recent work of Elba and Franz, where they proved this in general, they use a similar, I'm not super familiar with their work, but I think they use a similar setup in terms of lax operators. And I think, I don't know, maybe Reinier and Raphael know more, but yeah.
Okay, thank you.
Okay, so anyway, so the question here is, so the usual topological recursion calculates Alberta Hurwitz numbers, this is proved. And they satisfy this quantum curve, which is not the one we get. But also we don't expect to be the same because we calculate different WGNs, except for r equals to 1. For higher r, we calculate different WGNs. So what are we actually calculating? So this was a mystery until Reinier moved to the U of A, and then Quinten and I were explaining our work and says, well, I know what this is calculating. We're like, oh, you are cool, Reinier. So, and he says, well, I know what it's calculating because there's a work of Alexandrov, Shadwin and Danilo Lewensky, where they construct what they call Atlantes Hurwitz numbers. So it's another flavor of Hurwitz numbers. And they make, actually I have some quotes here, so let me show the quotes right away. They make a big point of explaining that this is cool because this is one example of enumerative invariance in the context of Hurwitz numbers that are not calculated by topological recursion. So we have an example where the dequantization of the quantum curve doesn't give a spectral curve suitable for the corresponding topological recursion. And they go on and on. So they're all excited to show that this is not a case where topological recursion works. But the point is that it is. It's just that they weren't using the right topological recursion. So, and that's exactly what we prove, is that the WGNs that the transalgebraic topological recursion calculate are generating functions for these Atlantes Hurwitz numbers. And indeed, in that paper of Alexandrov and Lewansky and Shadrin, they do show that these Atlantes Hurwitz numbers satisfy, or the wave function constructed from those is killed by this quantum curve, which is exactly the one we get. So our transalgebraic topological recursion has a nice enumerative interpretation as well, but it is different. It's now Atlantes Hurwitz numbers, not completed cycle Hurwitz numbers. Now, in genus 0, they're the same. For hard genus, however, they become different, and this is exactly what we observe from our construction. So I don't know, that's kind of cool. So we can tell them that they were absolutely right. It is not constructed by topological recursion in the usual sense, but it is constructed by the more general topological recursion. And that's kind of cool because these two cases here have the same spectral curve. It's just that in one case, you ignore the contributions from exponential singularities. And in the other case, the second case, you don't ignore them. And then you construct the full theory of Atlantes Hurwitz numbers. Okay, so this is the kind of enumerative interpretation of our construction in this particular case. And I guess I don't know what time I started, but I should probably end. I think I'm pretty much done anyway, so that's good. But conclusion here is that what we propose here is a new definition of topological recursion. So I've only focused in this talk on one particular family of curve, which was this R-spin family, but it applies much more generally to families with exponential singularities. So we have a definition of topological recursion that does have contributions from these exponential singularities, and by constructions and naturally commutes with limits of sequences of algebraic spectral curves. So we get for free a proof of topological recursion quantum curve correspondence for all these transalgebraic spectral curves, if at least the quantum curve is known for the sequence of algebraic spectral curves. And in this particular example, we can prove that our transalgebraic TR calculates Atlantes Hurwitz numbers, and we recover the quantum curve that was proved using combinatorial techniques by Alexandrov, Lewansky, and Shadrin. But that, of course, opens up a lot of questions. So this enumerative interpretation is fascinating, at least to me, in the context of that particular curve. But in general, what are we calculating? So if you pick a general transalgebraic spectral curve, can we write down an interpretation in terms of some sort of flavor, very general flavor of Hurwitz numbers? And that would be great to clarify this and get a very general statement here of what the generalization of TR is calculating. And the second point is something that's also quite cool. So as I mentioned before, for those of you who know about Hurwitz numbers, you know probably about this very important result called the ELSV formula, which says that you can rewrite Hurwitz numbers as integral over the moduli space of curves. From the point of view of topological recursion, you can prove ELSV in a fairly straightforward way, because what happens is you have the sequence of WGNs, and these are meromorphic differentials on the Riemann surface, but you can expand them at two different points. And if you expand at infinity, the coefficients of your expansion will be Hurwitz numbers, while if you expand in the basis of differential forms with pole at the magnification points, the coefficients will be the integral over the moduli space of curves. And the relation between these two expansions is the ELSV formula. So that's a proof of ELSV that from topological recursion. And now you could ask whether we can do something similar for Atlantes Hurwitz numbers. So in other words, what we would need is now to understand the enumerative interpretation for the contributions coming from the exponential singularities. Can we rewrite those as some sort of integral over the moduli space of curves, or potentially moduli space of curves with some sort of infinite spin structure? I don't know what that would look like, but that's certainly something that would be interesting to look at. And then, yeah, can this be generalized? So we only looked here at what we call transalgebraic spectral curve, but we still assume that W01 was meromorphic on the whole compact Riemann surface. But in some cases, you don't want even this. So not only do you want X to be transalgebraic, you also want W01 to have, for example, logarithmic, to be defined only on a surface with log cuts, so have logarithmic contributions in there. That's what happens, for example, for Grommelton theory of P1 and Grommelton theory of torical labial manifolds. So we are working on generalizing our framework to this using sequences of spectral curves. But yeah, that's work in progress. I don't have much to say about this. But but yeah, so I guess that summarizes my talk. So thank you very much for listening, and I'm happy to answer any questions you may have. Thank you.
Thank you for the very nice talk. So do we have any questions? If you do, maybe just raise your hand.
Well, I have a question if nobody. So, Vincent, you know that many years ago, and this is really just memory, I was looking at these notion of weighted Hurwitz numbers, and there was a weight generating function. And well, I was there for Danny Lowe's thesis, so I remember this business about Atlantes and R-spin and so on. And there was a question which was never quite clarified, but maybe you know the answer to that. And that is it possible to capture these R-spin and Atlantes type Hurwitz numbers using a suitable weight generating function in which possibly H bar appears explicitly?
I think Reinier could answer better than me, but I think that's exactly what isn't it what Shadrin and friends do in these papers, and Lewanski, where they, well, I don't know if they have, no, I don't know if they have a weighted generating function in the sense that you're talking about, but they do have these H bar corrections in there.
I would say that they do. Yeah, again, depending on what shape you want exactly, but there's this very general framework right now of Dunin-Barkowski, Kazarian, Bychkov, Dunin-Barkowski, Kazarian, and Shadrin, where they take a very large class of hypergeometric tile functions, which they define in terms of these weight generating functions of yours, basically, and show that in a very large class under certain pretty general assumptions on these weight generating functions, they get topological recursion. And in particular, they do this also for completed cycles. So they give explicitly the weight generating functions.
And they do need these H bar corrections, right?
Yes, the H bar corrections are essential.
And also Atlantes.
But not for Atlantes, they don't need the H bar correction. Actually, that's one of the main differences.
So what is the actual, so I've forgotten this, but what is the weight generating function for Atlantes?
I mean, that's a good question. I think it's really just the exponent of z to the r or something.
Isn't that the R-spin?
No, so for this R-spin, you need an H bar correction.
I think it's the same thing up to the H bar correction, right? I mean,
yes.
I just like the spectral curve is the same. So I think it's the same generating function, but for the R-spin, you need to correct it. For Atlantes, you don't correct it, if I remember was that.
Yes, that is definitely true. So for the R-spin, you need to, it's something like the exponent of y minus h bar over 2 to the power r or something. I don't remember the exact shape, but they get, so these papers I refer to, Bychkov, Dunin-Barkowski, Kazarian, Shadrin, they have some pretty nifty tables where they just give a lot of different generating functions, weight generating functions, and tell you what's the related Hurwitz type problem is, and these are particular cases they mention. Right, and it shows again, I mean, and kind of the moral, or the thing I was saying here is that somehow this formulation, this transalgebraic TR, is in some way more natural, because it calculates, in this case, Atlantes Hurwitz numbers, would be exactly what you get from the generating function without corrections. But to get the R-spin one, you need to correct it, just like you would have to remove the contributions from exponential singularities that should naturally be there. So it seems like, this is kind of it's more natural in my mind.
May I also ask, just on the behalf of the non-specialist part of the audience who have not worked on Hurwitz numbers or topological recursion, I think I knew this at one time. Atlantis means Atlas. I think it means it's just another word for Atlas, the Greek god Atlas. But can you remind me why? I think Shadrin coined that term. Why does he call it Atlantis?
Right. This is because what they use is blocks of Atlantes, as they call it. So you have blocks of R simple ramifications, all of whom are of the form, say, transpositions AI, B, where B is the same. So and AI is smaller than B. So you have to imagine So the way they draw it is always as, so if you draw a simple ramification, it's basically a crossing between two sheets. Then the idea is that this crossing somehow symbolizes a man holding up the sky, and if you have a block of Atlantes, they are holding up the same level sky. That relates to the myth of Atlas. That is their motivation for the term.
So I don't want to monopolize the question, but is it, you know, there are two ways to interpret the Hurwitz numbers, one in terms of enumeration of branch coverings, and the other is in terms of enumeration of paths in the Cayley graph. Mm-hmm. And if you look at paths, that's what gives the, you know, notion of monotonic and so on. But if you look at paths, you can also have sort of piecewise monotonic where you stay on the same level for a while and then you go up and so on. Is that what Atlantis means?
It's a bit like that. So they have blocks of these Atlantes, which is not quite. So maybe it's easier to express in terms of symmetric functions. So you have strictly monotonic is elementary symmetric functions. Weakly monotonic is complete symmetric functions.
Yeah.
And Atlantes are power sums.
Ah. Okay. Well, that says a lot. But that's in the covering interpretation, so I'm not sure what that means in terms of paths.
I'm also not sure what it means in terms of paths, to be honest.
Okay, thanks.
Any other questions? If not, let's thank Vincent again. Thank you for the very nice talk.
Thank you very much, everyone. Have a wonderful day, evening, afternoon, whatever.